So so if there is no issue, okay, let's make it one by one. Okay, let's make this topic one by. So let's make the decision. Okay, the next midterm will be November 13th. Okay, it's Friday. Okay, this is I want to make this decision. So if you have any issue with that, let me know earlier. Okay, so I can arrange some other time that's specific for you. And for the homework, okay, I know a lot of students think that because this right now is in the middle of the semester, I understand that, okay, because that this is usually the most busy time. And we have a homework will be due today. Some students write me an email to ask me to make an extension for the homework. I'm okay with that, but the only issue is that some students already submitted, okay? So if I make the extension for the homework at the last minute, it will not be very fair to the student who already submitted, because that they're supposed to have more time to to go through the homework. Okay. So what I'm going to do is that I can extend it just for very short time. I won't be able to give extended the homework for a week. No, this is not good to other students already submitted. Okay. So for this homework 3, which will be due tonight, I give you 3 more days. Okay, I will make it. I will change the due date to the Monday midnight. Okay, is that what works for you, everyone?
I think the homework is already due on Monday.
Yeah, it was originally.
Oh, it's already due on Monday. Okay, so I can make it due next Friday. I'm sorry, I make mistake here. I can make it due next Friday. Okay, so I won't be able to give you much more time for that. Okay.
Yeah, Friday would be very helpful. Thank you, Professor.
Okay. Okay. So let's make these 2 decisions. Okay. Midterm will be on the November 13th, and homework will be due on October 30th. Okay. So that's what I'm going to do. Oh, what is popping up? All right. So let's start today's lecture right now. Okay. And in the last lecture, right, we are talking about the differential form of the fluid dynamics governing equation, right? On the chapter 4, we developed the integral form. We developed those integral form for the mass conservation, momentum conservation, angular momentum principle, energy conservation. Those equations in the integral form on a control volume, right? But the integral form is useful, but it won't help you to solve what happens inside. Okay, the integral form is an integration form, right? So basically, it only gives you the all the things in a bulk. Okay, because in the integration form, it's only useful for you to study that the interface at the boundary surface. Like if you have if your control volume is contact with the wall, right? And for those example problem we covered before, like you want to determine that how much force between this control surface and the wall, those kind of things. But you won't able to know that what happens inside the fluid. Okay, you won't be able to know that inside the fluid what actually each local point, what the velocity, what the pressure, what the density, what the temperature there. All right, and that's why that we go to the differential form, and the differential form basically is that the equation we want to try to derive, right? Those fundamental law equations we want to try to derive, not for overall control volume, but for a very small infinitesimal fluid particle. Okay, and so that so if we can derive those kind of equations, so basically means that for each local point inside this inside the fluid, the particle at that time, located at that position, we have the governing equation for it. Okay, so that if we can solve this kind of differential form of the equation, we are able to solve that what really happened inside the fluid. Okay, and the way we derive the differential equation, in the last lecture, we used the mass conservation as the first example, right? And so it's still the same idea what we did in the chapter 4 for the integral form. Okay, but instead for the define the geometry, okay, of the control volume in the chapter 4, when we try to derive the integral form equation, right? We first define a control volume, and then we assume that control volume is fixed on location, not change with the shape, right? It's a big one. But in this when we try to derive this differential form, right? We define a, you know, a very small differential form of volume. Okay, we call it like it's a very small infinitesimal for this rectangular rectangular coordinate system, right? We define a very infinitesimal cube. Okay, it is a differential volume, and on this for this different volume, we still apply the same conservation laws, those fundamental laws, and we still apply that same thing similar to the chapter 4. Okay, we assume this is a small control volume. Okay, and for the mass, the change of the overall mass will be for the system will be just equal to the change of the mass inside this small control volume plus the net of mass flux flowing out from its control surface, right? So this is what we did here, and after we get that equation, we just write this the size, right, of this cube, this dx dy dz, go to limit, okay, limit to 0, so that the whole cube will be collapsed to a single point inside at the center of this cube, this O point here, right? So by that way, we get the differential equation which can working for this fluid at this point, right? And for this cube, right, for this rectangular coordinates, for this cube in this rectangular coordinates, right? When we try to derive this mass conservation, we have two terms, right? One is that the change of the mass inside this cube and inside this control volume is easy, okay? It's very easy to do. The dx dy dz is the volume, rho times this dx dy dz, and do partial t, okay? We can get what the change in the volume. But for the mass flux, okay, what is flow in and flow out? So we need to consider all the 6 surfaces, right? You remember what we did last time? And to derive this the value at this mass flux at this 6 surface, right? Basically, we need to know the density and velocity at each surface, and we get that one by using the Taylor series, right? So that we know that if we know the value at this center point, right, we get the corresponding density and the velocity at each surface using this Taylor series. And after that, we can derive that the mass flux for each surface. We add it together, okay, and we add it together and make the limit go to this control volume, this their size go to collapse to this point, and this will be the final mass conservation equation we obtain. Okay, you will see that it's not an integration form anymore. Okay, it's a differential form. That's why that we call this a differential form of the mass conservation. And we also know that this equation, okay, will work for this point. We for this for this single location point XYZ at this point for this fluid. And that is why that if we can solve this equation, basically we can solve what happens inside the fluid. Okay, and we also can write this equation in the vector form. Okay, so we have it contains 2 parts, right? So this part is called the change of the density, the rate of the change of density locally, and the second part is the divergence of this rho v. Okay, and this nabla operator is a vector operator. We call it the divergence, divergence operator. Okay, and it's defined by this. If you do delta dot velocity, it will be so basically this these things we call it the divergence operator, right? So this simply means that partial x, I plus partial y g plus partial z k. Okay, and then you apply this to a vector. Okay, so if it is v, then it will be ui plus vg plus wk. Okay, and then you do this dot product between them. This is dot product between this operator and this vector. You get this form. You get back to the original form here. All right. And what the advantage of this vector form is that we will show you later. Like this vector form, okay, will not limited to the coordinate system. Okay. So if we write this governing equation, this mass conservation equation in this vector form, rather than writing in this individual component form. So this same vector form can also be working for other coordinate systems like the cylindrical coordinates, spherical coordinates. The only difference is that this operator here, this divergence operator here may have different mass notation for different operating coordinate system. Okay, so this is what we have in the last class. Okay, so to further understand this differential form of mass conservation, okay, and we also do an example problem at the end of we do two example problem at the end of the last class. All right, and to continue from here, okay, we also try to do the same mass conservation equation. We try to derive the same differential form of mass conservation, but now, okay, we are going to do it on a small, very infinitesimal small fluid particle, but inside of a cylindrical coordinate system. Okay, so assume that we have a cylindrical coordinate system, which is coordinate can be written in the r, theta, and z, right? R is radial, theta is azimuthal, and z is vertical, and theta it can be from 0 to pi, of 0 to 2 pi. And how we define that in this small control volume, this differential volume for this coordinate system. It's same thing, right? Remember that in the rectangular coordinate system, we define this small differential volume by using dx, dy, and dz, right? dx is a small change on x, dy is a small change on y, dz is a small change on z, so that we know that this volume will be a cube. All right. So it's similar things, okay, in this cylindrical coordinates. So when we try to define this control volume, right, we also like this r. This is the r direction, right? Go to make a small change on this r direction. So this will be dr. Okay, and also that we make a theta also do a small change. So this angle will be d theta. Okay, and also on the similar thing on the z direction. On this z direction, we also make small change on the dz. Okay, so by doing this way, okay, we can also draw this 3D, small differential control volume for this coordinate system. All right, you can see that this will be, I don't know how to write. So it's an annular sectional, body, something like that. Okay, and so now we are trying to, try to derive that what's the mass conservation for this small control volume. It's a similar thing, right? We consider two terms. We consider the terms like a change of the mass inside this control volume with this one, and we also need to consider the change of the mass, okay, across due to the mass flux across all the surfaces. This one plus this one should be 0. That is the mass conservation. Okay. For the first term, it's simple. It's very simple because this can be just give you like this is the change of the density and times the volume. Okay, so what's the volume for this small control volume? How we calculate the volume will be? So we just need to using this length here times this length and times this length, right? And this is d theta and this is r. So this length here actually is r d theta, right? So this is d theta is this angle, and we assume this is this from origin to here. This is the radius length r. So this will be r d theta. So the volume, okay, dV for this one will be given by r d theta times this dr and then times dc. Okay, so this is what the volume for it. This length times this length times this length. Okay, so that's why is that if you want to calculate what the mass changes inside this control volume over the time, you can just given by go to this one partial rho partial t and r d theta dr dz. And this one is the dV, okay? This one is just this dV here. So rho times dV give you the mass changes. And so how about the next term, right? We need to consider this surface mass flux for this cylindrical coordinate system, right? And so we just need to similar thing, okay? You can do using the Taylor series to get what's the density, what's the velocity at each this 6 surface. And then you just multiply them to get what's the mass flux at all these 6 surfaces. Okay, And the procedure will be similar to what we did earlier, you know, what we did earlier here for the match flux on the left, left flux for the right, bottom, top, front, end, from front, back, okay, when we do in the rectangular coordinate system, okay. And here we do not need to, repeat this procedure, okay, but the result is also given in this table form, okay. What's the inner surface? This is the minus R direction. What the mass flux will be? So this is the density at that surface, and this will be the velocity at that surface. Okay, what's the outer surface? Positive R phase, same thing, and negative theta phase, positive theta phase, and negative Z phase and positive Z phase. So by this way, we can derive that what's the mass flux at all these 6 surfaces. And then you just need to add them all together. Add the mass flux all them together, so you can know that what's the net mass flux across the whole control surface. Okay, so when you add it together, this sum term will be cancelled. This will cancel, this cancel, this cancel, and the only thing left is will be given here. Okay, this is just pure math. Okay, and you can rearrange what is the result you get, and you can get this final result here. Okay, so in another word, it will showing you that okay, the net rate of mass flux will be equal to this one. Okay, and remember that the principle of the mass conservation basically is this term plus this term equal to 0, right? So now we can derive that what is this differential form of mass conservation for this cylindrical coordinate system will be this one plus this one equal to 0. Okay, and by doing that, so we can get the final result. So this one plus this one equal to 0, and we also canceled all this dr dc theta dc, okay, terms. So just divide it on the both sides, and we get this equation here. This is what we can get, and this is from the surface flux, and this is from the changes inside the control volume. Okay, and you can further rewrite it. Okay, rearrange it. For this one, we put it, we make it inside here. Okay, and then you divide it by R on the both sides. We can write this, it will be the final form. So this is the differential form of the continuity equation for the cylindrical coordinate system. All right, you'll see that it's pretty different than the form we get for the rectangular coordinate system. Okay, and also remember that this VR, V theta, Vz is the velocity on the R, theta, and Z direction. Okay, so this is what we have here, and for this equation, we can also write it in the vector form. Okay, and the vector form using that divergence operator we introduced before. And for the cylindrical coordinates, okay, this divergence operator can be written in this way. Remember that this divergence operator in the rectangular coordinate is we write it in this way: part of x, part I, part of y, j plus part of jk, right? So it's just that this divergence operator in the cylindrical coordinate will have a different form, will be in this form. And by this way, okay, so we can rewrite this continuity equation in the vector form for this cylindrical coordinate system. It will go back to this one, the divergence of rho v plus partial rho partial t equal to 0. And what this one? This is, if you write this in the vector form, you will see that this is the same equation we have for the rectangular system. Remember, for the rectangular system, we also can write the vector form in this form. So that's this showing you that why we want to write this thing in the vector form, because that if we can write this in the vector form, we can make this equation independent on the which coordinate system you use. Okay, you see that this equation working for both rectangular coordinates and cylindrical coordinates. Okay, so which means that they are universal. But the only difference is that if you want to write from this vector form to the component form, when you write this divergence operator out, then you may need to using this expression for this divergence operator for rectangular system or for the cylindrical system, will be different. Okay, so this is why we want to write in the vector form. Okay, and so this equation, when you look at it, right, you will feel like this is more mathematically is more complicated than the equation we get for the rectangular coordinate. Okay, but we can simplify it by make some assumptions here. Okay, the first assumption we can make is that we can make this assume that in the case is when rho equal to constant. Okay, which is if we assume the flow is incompressible, what we have. Okay, if the flow is incompressible, rho is constant, this term is gone, partial property is gone, and then this rho you can take it out from this differential, and you can remove the rho from the both sides. The equation will become this one for incompressible flow. And again, this one is just exactly the based on this divergence operator we have here. Okay, so we can also see that this can be read in this one. It's showing that we can also see that this for incompressible flow, it just means that the divergence of the velocity vector equal to 0. Okay, and for the steady flow, it just means that that transient term is gone. Just means this transient term is gone. Okay, and so we can write the result in this form equal to 0. And this one again can be read in the vector form. Will be divergence of rho v equal to 0. Okay, so what you find, so similar to the vector form for the whole equation, okay, which means that this vector form will be, independent on which coordinate system you use. You will see that same will happen here for these two special cases. For the incompressible flow, this divergence of v will also working for both rectangular coordinate and cylindrical coordinate. And if you have this steady flow, this divergence of rho v equal to 0, this one is also working for both rectangular coordinate and cylindrical coordinate. Okay, so that's showing you that how powerful this vector form will be. And this is how we derive this differential equation of mass conservation. Okay, for the for all the two different coordinate systems. Okay, rectangular and cylindrical. And to practice it, okay, we have an example problem to practice this continuity equation in the cylindrical coordinates. All right, and this example problem is a simple one. Okay, it will be a one-dimensional flow. Okay, which means that one-dimensional flow only in the radial direction, right? So which means that the velocity is only on the r direction. Okay, so that's why is that let's assume that this r direction velocity is as a function of fr. Okay, and this showing on this r theta plane, which means that this is that is not happening on the z plane. Okay, so which means that is that the partial z term can gone. Okay, and the velocity is only on r, which means that velocity on theta equal to 0. Okay, and the question you're asking us that from the continuity equation, how we know what form of this fr, this velocity fr, can satisfy the continuity equation if the flow is incompressible. So it's pretty straightforward. Okay, so first you just need to write out that what's the differential form of the continuity equation, okay, for this cylindrical coordinates, and also that only 1D flow on the r direction. Okay, so this is the incompressible flow for cylindrical coordinates. It's one-dimensional flow only on r, so that this term is gone, and because theta is always 0, so v theta is 0, so this is gone. So the only thing left is this one. Okay, 1 over r partial r times vr partial r equal to 0. Okay, so we have this. So this is the only equation we have. Okay, and just substitute this fr into it. Okay, and you just you substitute this fr into it, and then you integrate it for this equation on r on the both sides. You try to find what this fr will be, right? So you're showing that this r times vr after your integration on r by 1 time, it must be equal to constant, and because this vr is this fr. Okay, so which means that telling us that for if you want to have this one-dimensional, incompressible flow in this radial direction, your r direction velocity has to be in this form. This constant divided by this r should be, and this c is some unknown constant. Okay, so this is telling you that this is the only possible way for this velocity on the r direction for this kind of problem to satisfy the continuity equation. Okay, so this is just one simple example problem for you. All right, and now we developed the differential equation, right, for the mass conservation, or you can just call it continuity equation. And our next task is to find that what's the differential form equation for the momentum equation, right? And what is the momentum equation? We know that the momentum equation is coming from the Newton's second law, right? So basically, the momentum equation will determine the flow motion, right? It will give you the flow motion because Newton's second law is giving the motion, right? And to do that, okay, to do the momentum equation, right? And we will do it in two parts. Okay, we will do it the fluid motion in the kinematic part first, and then we will do the flow motion on the kinetic part later. Okay, so what is the kinematic part? Kinematic part is that we just study the motion of the fluid. Okay, without consider the force, right? This is what you learn in the dynamics, right? And the kinetic part will come later, so that we can relate the Newton's second law with the motion. So the first thing is the kinematic part. So we want to know that there's a way to describe the flow motion. Okay, so so in this differential form, how we get this velocity, position, velocity, acceleration correlation for the fluid particles. Okay, and so let's first start from a concept called the stream function. Okay, so this one is closely related to the mass conservation. Okay, after this one we'll go to the momentum equation. Okay, and so first thing, okay, let's recall that what we learned in the chapter 1, the stream function, right? So what is the definition of the stream function? The stream function we define is that at any local point, right, at any instantaneous time, the tangent direction, the tangential direction of the streamline will be just equal to the local velocity direction, right? So if this is streamline here, and if I want to go to this point here, and the tangent direction with this streamline will be just the same direction with the velocity v direction. Okay, assume that this is y of x, and this is x, and this is y. Okay, so this will be, so this length is x, and this length is y of x, right? And so what their tangent direction is determined, right? So the tangent direction is given by dy dx, right? So this is tangent direction dy dx. And also, if you decompose this velocity into two component forms, so this will be u, and this will be small v, right? And the tangent direction can also be given by this v over u, right? Because this is given this tangent theta. Okay, and so in another word, we can define that a streamline, so that at any, if we can find this function, right? Because we want to find this streamline function, right? So if we can find this y equal to yx, this curve, so that this dy dx, which will be tangent of this any point on this curve as a streamline, will be just equal to v over u, right? V over u. This will give a tangent direction. So this is the definition of the streamline we have in the chapter 1, right? And so we can rearrange this equation a little bit. We times u to here, we times dx to here, so that along the streamline we have this satisfied u of dx dy minus v times dx equal to 0. Okay, and so let's assume that we can define a new function. Okay, we call it the psi of xy. Okay, let's assume that we define this new function called psi of x1, and the way we define it is like we make this partial psi partial y equal to u, and minus partial psi partial x equal to v. You may ask me that why we define this function. I'll show you later why we do that. Okay, just assume that we define this psi that satisfy. So the way we define this psi is by solving these two equations. Okay, and so if we can define this psi in this way, and since u equal to partial psi partial y and v equal to minus partial psi partial x, right? You can just substitute this value into this equation, right? Remember, this is satisfied on all the points on the streamline, right? So you start substitute these two into here. So what do you get? You will get this, partial psi partial y times dy, right? This is u, and the minus, you have minus will become plus. Partial psi partial x times dx equal to 0. You get this form. And this is partial derivative, and then you have this dx dy. This will be changed to the, regular derivative, total derivative. It will become d phi equal to d psi equal to 0. So what does this mean? So that means that if we can define a new function in this form, then this function, the value of this function on the streamline, right? Remember, this is only valid on the streamline, and we substitute here, and we get this d psi equal to 0, right? So which means that if we can define this function here, and this function on this streamline will become a constant. Because d psi equal to 0 telling you that psi equal to constant, right? So which means that psi is constant on this streamline. Okay, so which means that if you have many streamline here, right? For example, you have the second streamline, the third streamline. So maybe for this streamline here, the psi will be just equal to psi of 1, a constant value, and in the middle will be psi equal to psi of 2, and in the third of psi equal to psi of 3. We can do that for because the value, if we can define this function value on each streamline, they will become constant, and this constant may be different. Okay, but along the same streamline, they will be the same constant. Okay, so which means that we can using this psi function to describe the streamline. We just think that if we can solve this, there is a way we can find this psi of xi for the whole xy domain. Then we know that what the stream function will be. The stream function will just be this xy to be constant on some line, right? And then this psi xy give us a mathematical definition of the streamline. Right? Previously, we do not have a mathematical definition for the streamline. We just knowing that this correlation. But when you try to draw this streamline, you don't know how to draw it. But now, after we did, introducing this psi function, so we know how to draw it, because that if we want to draw the first streamline, we just make the psi xy equal to 0. I want to draw the second streamline, just make this psi xy equal to 1. I draw the second streamline, right? And then we call this psi xy. We call this function give a name for it. We call it stream function. Okay, so just think about that. This stream function is just the way to define the local streamlines. Okay, when this stream function equal to constant, it gives us one streamline. All right, and so the important thing is that how we define the stream function, right? It's just coming from these two equations. Okay, so it's just coming from these two equations. So this is the definition of the streamline. So this is telling you giving us the procedure that if you have a flow field, right, and if you want to visualize this flow field by the streamline, how you do that? How you do that? You just need to find that solve these two equations, because you already know that what's the velocity at the flow velocity at all the points, right? Fluid points. Then you just solve these two equations to try to find this psi as a function of xy. Then just make the psi of x to some constant value. You can draw corresponding streamlines for it. Okay, so this is the meaning of the stream function. Okay, but this stream function, okay, I will show you later on that you cannot just define it arbitrarily. Okay, It's not the case is that all the fluids have the stream function. Okay, this stream function the way you can define this stream function is only working for limited cases, not for all the fluids. So what that limitation will be? Okay, so let's go back to the continuity equation. Okay, so if this U equal to partial phi, partial y, partial psi, partial y, right? And V is minus partial psi, partial x. And so if we define like this du dx, what do we get? If you give you what? If you give a partial psi, partial x, partial y, right? And then if we define this dv dy, what do we get? We get minus partial psi, partial x, partial y. So if you compare these two, what do you see? This is negative, this one, right? Yeah, in other words, so if you're using this one plus the second one, sorry, this V. If you're using this one plus this one, what do you get? You just get this result. Partial U, partial X, plus partial V, partial Y equal to 0. So what is this? What is this one? So consider that we have flow. This flow is in the two-dimensional, right? Because that we define the streamline only on V and U. So this is a two-dimensional flow. And what is one? This is the mass conservation with the equation we just derived in the last lecture, right? So this is the differential form of mass conservation when the density is constant for incompressible flow, right? So this is what we have before. For the incompressible flow, we have this one, right? This is the for incompressible flow. This is a different form of mass conservation. And if it's two-dimensional 2D flow on xy, let's remove this term. Partial ux, partial u, partial x plus partial v, partial y equal to 0. We got it here. So what does this mean? This means that this definition of the stream function will automatically satisfy this two-dimensional incompressible flows continuity equation. So in another word, okay. So if you want to define the stream function in this way, your flow has to be this two-dimensional incompressible flow. Okay, so which means that this stream function definition is only valid for this two-dimensional incompressible flow. Why? Because that if it's not two-dimensional incompressible flow, and if you still define this stream function, you will still get there, but you know that your mass conservation is different than this form. So this one should not be satisfied. So you know that this definition you made for the phi, for the psi is not correct. Okay, so at the end, okay, I just want to let you know that this stream function we defined here using this definition, okay, it limit only for the flow. This satisfies these two conditions. First, the flow has to be two-dimensional. If it's three-dimensional, you cannot define the stream function in this way. Second, it has to be incompressible flow. Okay, rho equal to constant. Okay, if its flow is not incompressible, then you won't be able to get the stream function for it. All right. So this is how we define the stream function for this two-dimensional flow, two-dimensional incompressible flow, and also that was the limitation of it. Okay, it's only working for the two-dimensional flow and incompressible flows. Okay, and do you guys have any question here? Anyone? No question? Okay, so let's continue. So we already know that, okay, so if you want to define the stream function in this way, not this way, sorry, stream function in this way, and it has to be satisfied by these two conditions. But what if our flow is not this one? Okay, for example, that what if our flow, okay, is let's assume that if our flow is a steady state flow, two-dimensional steady state flow, but it may be compressible. Okay, so rho is not constant. So this is our continuity equation, right? So this is our continuity equation. And so for this one, we can still define the stream function, but how we define it? We need to define the stream function in this way. Previously we have u part equal to partial y, partial psi, partial y, right? V equal to minus partial psi, partial x. Now you have to define your new stream function as rho u equal to partial psi, partial y, and rho v equal to minus partial psi, partial x. So by this way, if you define this way, so by this definition of the stream function, it can working for the continuity equation. It also satisfies the original this correlation here, because that you just have an additional row here, and then you can just divide it on both sides. Okay, so that it's also possible to define a stream function for two-dimensional steady-state flow, even the your flow is compressible, your rho is not constant. But at that case, when you define the psi, you have to using this new definition here. Okay, and similarly, okay, for the cylindrical coordinates, let's assume the two-dimensional flow incompressible. Okay, so we have this two-dimensional flow incompressible for the rectangular coordinates, right? For the cylindrical coordinates, you can also define the psi function in this way. Okay, VR equal to 1 over r partial psi partial theta, v theta equal to minus partial psi partial r. So that this definition will satisfy both the continuity equation, this one, also satisfy the definition of stream function, this one. Okay, so this is just some knowledge for you. And now we have to understand what the stream function, right? Basically, stream function is a mathematical description for the streamlines. Okay, when psi equal to constant, it gives us one streamline. But what is the physical meaning of it? Right. So let's assume that the case is that we have three streamlines here. The first streamline, the stream function is psi1 constant. The second streamline, we know that psi equal to psi2. And on the third streamline, we know psi equal to psi3. Okay. And now let's consider that let's consider these two streamlines, this psi1 and psi2 streamlines. Okay. And first, okay, if we consider the volume flow rate, okay, across this AB, okay, this AB line is actually the vertical one. Okay, so along this AB, actually x equal to a constant, and this AB along this AB line, only y is not changing. Y is changing. Okay, so in this way, if we want to calculate the volume flow rate across this AB line here, okay, so it just be equal to q time, because that is the normal direction is only u velocity, right? So it will be u times this dy and integration from y1 to y2, and assume that we have 1 unit depth on this vertical direction perpendicular to the screen. Okay, on this screen direction. And so this is how we calculate the volume flow rate on that one. Okay, and since that this u is given the definition partial psi partial y, okay, this is the definition of the stream function, do it. And also we know that along this y1 to y2, along this cable, along this line A and B, A to B, your x is not changed. So your so that which means that there is no dx. Okay, dx to 0. Okay, so that's why we neglect this integration on the dx term. Okay, so only thing left is on dy. Okay, and you integrate this one. Okay, and psi. So you will know that it gives us that the volume flow rate across this line AB will be equal to phi2 minus phi1. Okay, and similarly, okay, so we can try to calculate what's the volume flow rate across this line B and C. So this one is that it's a change from x1 to x2, but on the y direction is that there are no changes on the y direction coordinate. Okay, so it just integrate. So for this one, we just integration on the v, because the velocity is on this v direction here across this this line here. It will be integration from v times dx for the volume flow rate, from x1 to x2. We didn't do the y direction integration because that this y direction coordinate is not changing. Okay, and you bring the definition of the stream function, because v equal to minus partial psi partial x. Substitute here, you get the same result. It's showing you that okay, the volume flow rate across this AB line is phi2 minus phi1. Across this BC line is also phi2 minus phi1. And also that if we have an arbitrary line, like this arbitrary cable here, and since this cable, sorry, not cable, this lines, this ED here, right? You can always, project this ED as two, as two like two projection, one projection on the y direction. Okay, you do this y, so one projection on this y direction here, y direction. Another, sorry, not on this projection here. Another projection on this x direction here. This projection, y direction projection, x direction projection here. So maybe I should not use this projection way. Okay. So because that we can write this, this is how should I write it? So maybe I can write it in. If we have a line here, okay, because the mass flow coming here, volume flow rate coming from this line will be same coming from here, and it's also same one coming from here. We need to realize that on this streamline, right, the way we define the streamline is that the velocity, right, is only in the tangent direction of this line. So which means that there is no vertical velocity, right? There's no vertical velocity perpendicular to this line, to all these streamlines, because all the velocity is only in the tangent direction. So there's on this direction here, there's no velocity. On this direction, there's no velocity going there. All the flow velocity is only in this line, or in this in the direction parallel to this streamlines. So in another word, okay, so there is no mass flux across the streamline. Mass flow is only, your flow motion is only between the streamline. There is no flow across the streamline. Okay, so that's why is that the volume flow rate from here and from here, they're same. Why? Because that we know the flow has to go to here and then leaving from here. There's no flow can cross this boundary because this is the streamline. No flow can cross the streamline, right? And so that's why is that no matter which direction you get the same result, because they will all be equal to the same mass of volume flow rate that across between these two streamlines. All right. So yeah, another word, okay. So what's the another important physical meaning of this stream function is that the volume flow rate between the two streamlines will be just equal to the difference of the two stream function values. Okay. So if I want to, if I know the streamlines, this psi1, psi2, psi3, okay, and if I want to know the volume flow rate between these two streamlines, then we know that it will be psi3 minus psi2. And I want to know the streamline between these two lines. We know that it will be the volume flow rate between these two lines will be psi2 minus psi1. And what is the volume flow rate between this psi3 and psi1? Then you just psi3 minus psi1. Okay, so this is another physical meaning of the stream function. Their value difference give you the volume flow rate between the streamlines. Okay, the volume flow rate between the two streamlines, okay, is given by the difference of the two stream function values. Okay, and so this is one thing. So the second thing we can observe is that so if you draw the streamline, okay, so let's assume I have one streamline here, one streamline here, one streamline here. Okay, at this part, like your streamline is more, sparse, to keep too far away, far apart to each other. And at this part, your streamline are more close to each other. And from this visualization, we can immediately knowing that the velocity at this region will be much larger than velocity at this region. Why? Because that we already know that the volume flow rate is same, right? From this, the volume flow rate between these two streamlines, the volume flow rate here is same. The volume flow rate here, volume flow rate here is same. But we know that the area, the distance, the cross-sectional area here is much larger than here. And if we want to have the same volume flow rate, the velocity here must be smaller than the velocity here, right? So based on this, we knowing that this streamline difference give us the same volume flow rate. Okay, we can also knowing that if you have this streamlines, right? So if these streamlines they try to become more closer to each other, are close to each other, then we know that their velocity will be higher in that region. And if your streamline is more, sparse, are kept far away to each other, then we know that the velocity there should be relatively lower. Okay, this is also some, some way you can analyze from this stream function streamline. Okay. Right. So this is another physical meaning of the stream function. So let's summarize what we have for the stream function. Stream function is only for the two-dimensional flow, and only for very limited cases for the two-dimensional flow. Either we can define the stream function for the two-dimensional flow of incompressible flow by using this way, or for steady flow, or for steady state flow using this way. Okay, and the stream function gives us a mathematical description for the streamline, because that when stream function equal to constant is just a streamline. It's also telling us that your stream function, the difference between the two streamline, the stream function values of these two streamlines just give you the volume flow rate between these two streamlines. That's it. Okay, so this is all the meaning of these stream functions. Do you guys have any question for this stream function? No question? Okay, so if there are no questions, let's try to solve a problem, like try to derive what the stream function will be. Okay, and consider you have a flow. Okay, a flow in a corner. All right, and assume that you have a flow here. Okay, you have flow flowing out, so either you're moving like this way, or you have another one. So this is wall, or you have another wall here, like you have flow going out, going this way. And let's assume that we know the velocity, field will be, the velocity field is equal to ax times I minus ay times g. And this a is a constant given as a 0.3. Okay, so the question is asked us that on this xy plane, okay, let's assume that this is x and this is y. Okay, so this is the one problem. We call this problem is quarter 2. Okay, so this is quarter 2, q2. This is q1 quarter. Okay, so for these two different cases, so what the stream function will be? It's pretty straightforward, because that for this one we assume that incompressible, two-dimensional incompressible flow, right? So that means that we can directly using this concept to derive the stream function. This is the definition of stream function for this incompressible two-dimensional flow. Okay, and so which means that u will be partial psi partial y. Okay, and u is what? U is just ax, right? So this is the velocity component on x direction. So ax is to partial psi partial y. And how we get psi from it? So we just, if we want to get psi from it, we just integration is partial psi partial y on y. Okay, and then we know that this integration result must to plus an arbitrary fx, because this is only give you the dependence of this psi on the y direction. It doesn't give you any dependence on the x direction, right? So which means that after you do this integration, you have to add an arbitrary function, which is a function of x only, so that we can get this psi here. You substitute this partial psi partial y as this ax here, you know that, and then integration on dy, you get this axy. Okay, this integration constant, okay, it will be a constant function fx. Well, it is only dependent on x only. Okay, and then how to find this unknown function fx? This fx is this integration result from this partial integration. Okay, because this is not a direct integration, so that's why you have this, unknown, constant unknown function of fx here as this integration result. And to find this fx, then you go to v, because v equal to minus partial phi partial y partial x. You substitute this one into this equation, you get what? You get that this a minus ay minus partial phi f partial x will be equal to v. And what v it is? V equal to minus ay. So this will be equal to minus ay. And minus ay is cancelled. So you get that you are minus partial f partial x No, not partial, because this f is only function x. So the df dx equal to 0. You get this df dx equal to 0. So in another word, this f has to be a constant. Okay, so your stream function will be what for this problem? So the stream function will be psi equal to this axy plus a constant c. So this was the stream function for the whole flow field. Okay, so this is the unknown value of c here. This is not unknown value. This is the constant value of c. Okay, so how we use this? Okay, usually, okay, from our the traditional way we did, okay, the most popular way we did in the fluid mechanics is that we always assume that the flow, okay, at the wall, the stream function at the wall equal to 0. We always like to make, so if this is origin point, okay, so this is O, and this is Y, and this is X, or this is O, this is X, and this is Y, okay. We always like the streamline, because that this is solid wall is also a streamline, okay, because that at the solid wall U equal to 0, V equal to 0. It's also satisfy this satisfy this partial phi partial y u equal to partial psi partial y v minus partial psi partial x. Okay, you can add wall u equal to v equal to 0, which means that the partial psi equal to 0, partial y equal to 0 for u, minus partial psi partial x for v equal to 0. Okay, from this way, okay, which means that giving us that psi will be constant at the wall, right? Remember, so this is from u and this is from v, and both sides on y on x they're all 0, so which means psi is constant on wall. So which means that the wall is also a stream function, right? Because psi is constant at the wall, right? So the usually traditional way we did is that we want to make the stream function value at the wall will be 0. Okay, so if you substitute here at this wall, x equal to 0, y equal to 0, you want psi equal to 0. So the only way is give you c equal to 0. So psi equal to 0 at the wall. So this is just some, the the regular way, the way we likely to do the most. Because that why we do that? Because that you from this definition, from this explanation we give here already, it's showing you that the difference of the psi value, right, give us that the volume flow rate. So which means that the absolute value, okay, in the flow field, the absolute value of this stream function is not important. We do not care the absolute value. We only care that the relative value between different lines. Okay, because that this psi 2 minus psi 1, psi 2 minus 3, psi 3 minus psi 2, psi 3 minus psi 1, they give us that the volume flow rate. So the important thing is this the difference value between the streamlines. The value, the absolute value itself, okay, this can be 100, this can be 50, this is fine. I can also define this is 100, this is 150, this is fine, no problem. As long as the difference is between these two is 50. Give us the same volume flow rate. Okay, so in another word, it is like this c value. Okay, when you derive this psi function, this c can be anything. Okay, it doesn't matter because the absolute value of this psi is not important. The important thing is this the difference between the two streamlines. Okay, so this c can be anything. But to make our math more clean, okay, we have a traditional way. We usually define that we choose this c so that this psi at the wall will come to 0. That's the traditional way we did. Okay, so by using that one way, we can find c equal to 0. So your psi is just equal to axy. Okay, and a will be 0.3. So this will be a stream function. Okay, after you get this stream function, you can try to obtain, you can draw your streamlines. Okay, on this quarter one here, you can draw the stream function as this way. Default for each line, you can choose a different psi value. Psi equal to 0.3, 0.6, 0.9, 0.12, and remember psi equal to 0 is this line here. Okay, and on this second quarter, okay, because this u is smaller than 0, and v is also smaller than 0, so for these cases you have negative psi value. So you can also draw different streamline for these cases if the flow going to corner in this way. Okay, So this is an example showing you that how to calculate the stream function from the velocity field. All right. And do we have any question here? Anyone? So just remember that this stream function is really limited, okay, for several cases, only for two-dimensional flow. For three-dimensional flow, we do not use stream function, okay. And also stream function is only working for, you know, incompressible flow or steady flow, you know, and based on each flow you use, they have different definition for stream function. And the physical meaning of the stream function is that, you know, stream function give you the streamline, you know, when on streamline, stream function is constant. The second thing is that the difference between the streamlines give you the volume flow rate between the streamline. That's it. Okay, and mathematically, how to calculate the streamline from a velocity field is given by this example problem. You just first integrated on the u, you know, so that you know you get the psi, and then get this function, and then you determine this unknown fx from the v. Okay. Any question so far? No. Okay, so no question. Let's move to next topic. So now we are going to move into the momentum equation. First, we study the kinematic part. Okay, just try to guide those motion parameters for the fluid particle. We try to define that how we get the acceleration, velocity, and position of the particle. Okay, so this and assume we have a very small fluid particle. Okay, and this is defining this differential volume, differential control volume, dx dy dz here. Okay, is a finite element and infinitesimal particle. Okay, at this time equal to t, and after some time interval delta t dt, and it will move to a different position, right? It will move to a different position, and not only the position is changed. Okay, we can see that their velocity acceleration is also changed, as well as their shape. You see that originally is a cube, right? But because it's fluid, okay, and at this time at time t plus dt, the shape will not keep the same shape before, and also their orientation is also changing, right? So there is will be some kind of rotation to it. Okay, so if we want to study this, you know, what happens for this fluid particle after the motion, okay, for after the flow motion due to a small time interval, we need to consider the several, you know, elements of it. The first thing, we need to know that what's the translational motion of it, right? Because this is the position, location is translational moving to here, right? During this translational motion, we want to know that what's this translational distance, what is translational velocity, what this translational acceleration will be, right? So this is for the translational motion, and also that we know that you know, this phase originally going up, right? Now this phase go to here, okay? So there will also some kind of rotation of the problem, not only translational, also there's some kind of rotational can happen, right? So we also want to study that you know, during this process, what the rotation of this fluid particle will have. Okay, and the last one, not the orientation is changed, also the shape itself also changed, right? This is a cube, and now this is a you know, the shape is a deformed shape, right? So that we also need to consider the fluid deformation. Okay, and for the fluid deformation, we usually have two kinds of deformation. The first kind of deformation is called the angular deformation. Angular deformation means that originally here is 90 degrees, and now the shape is changed so that the angle between these two edges is, you know, is changed, not at 90 degrees, right? So originally it's here, now it's removed to something shape like this way. Sorry, not this way. It becomes something like this way. Okay, so this is called the angular deformation. Another deformation is called the linear deformation. Linear deformation is what? Linear deformation is related to the expansion or contraction. Okay, so original size is this one. Okay, maybe after it's moving to delta t, it become very big. This is enlarged, or maybe original this one, and then it become very small, contracted. Okay, so this maybe this also has this linear deformation, not only this angular deformation also, but also linear deformation. Okay, so if we want to have a full, description for the fluid motion, the motion of this small fluid particle, okay, we need to consider all these three major elements. Okay, you need to consider the translational motion of this fluid particle, the rotation of this fluid particle, and the deformation of this fluid particle. Okay, so you need to consider all of this. And so to using a picture to further to showing you that what this means, okay, is that so if we have the fluid motion, right, this is the location at the t, and this is location at the delta t, t plus dt, and we can decompose the fluid motion, the motion of this fluid particle in this time interval into 4 elements. The first element is translational motion. The second one is rotation. The third one is angular deformation. And the last one is linear deformation. Okay, so we will study each one to see that, so what's the mathematical description for linear motion? What's the mathematical description for the rotation, and mathematical description for deformation? After we have all this mathematical description for the kinematics of this particle, then the next step we can involve the, Newton's second law, because Newton's second law is F equal to ma, right? After we know this, how we write this a for all these three, because all these three will contribute to this a parameter acceleration. We have the translational acceleration, you have the rotational acceleration, you also have this deformation for this acceleration part. Okay, and after you're able to describe this kinematic parts for the fluid motion, then you can involve this Newton's second law, and then you involve all the force term, you can derive the momentum equation, right? So this is the whole procedure what we are going to do next. Okay, so the next several topics is that we just study all these 4 stuff one by one. Okay, and the first thing we are going to study the translational motion. This is the most simple one, right? We want to see that how the fluid particle is moving into translational. So translational motion, okay, we do not care about the rotation, we do not care about the deformation. So we can just collapse this particle to a single point at the mass center, so that we can just see that the mass center of this particle is moving from one location to another location, and we can, from this displacement of this mass center, we can know that what the velocity and what the acceleration will be. Okay, so let's first think about that fluid translation. Okay, the translational motion of the fluid particles. Okay, let's assume that this is the path line for this fluid particle. Okay, and assume that at the time equal to t, okay, this particle has a position vector r, and at the time when the time become t plus dt, okay, and their position vector is also changed, become r plus dr, right, become here. Okay, so now let's take a look at this particle here. So we can also have that at this t equal to time equal to t, right, this particle will have a velocity. And remember that in this Eulerian description, right? Because in this fluid mechanics, we're using Eulerian description of the fluids, right? So this v here is a function for x, y, z, t, right? So this is a velocity field. We call this a velocity field. Remember what we did before, right? For Eulerian field, your v will be right in the form of x, y, z of t, right? Because we measure this velocity on location. We not measure this velocity for moving particle. But for the Lagrangian, this v is only function of v of particle of t, right? So this Lagrangian, because Lagrangian method is like we measure the v followed by this particle, right? So because that in the flow field, fluid mechanics, we're usually using the Euclidean description. Okay, so your velocity, we only know the velocity field, and if we want to know the velocity of this particle at this time equal to t, so we need to substitute that, at this moment, what's the x, y, z value for this particle, and also put at t here. Okay, so this will give us that at time equal to t, what's the velocity of this particle. Okay, and similarly, okay, when t becomes dt, this particle will move into a new position, and then the velocity for this particle at t equal to plus dt, then you using this velocity, same velocity field, you have to replace this x with a new x plus dx, replace this y as new y plus dy, replace this z as new plus z plus dz, and similarly t plus dt. You have this one. All right. So the difference, the velocity difference changing from for this particle from this t to t plus dt during this small interval dt here, okay, it will be just equal to this one minus this one, right? So when you're using this one minus this one, what do you get? You will get with this value minus this value, and you'll see that this v velocity field has 4 independent components, and you have these changes for each independent variables. Okay, so you can actually write your difference, velocity difference, okay, by using this chain rule. Okay, so the change of this velocity for the particle will be just equal to the change of this velocity on the x, and then times the change of the x for this particle, plus change on the y times the y particle, change on the z particle, and change on the t times this t dt here. Okay, this is the chain rule here for this partial derivative, between the derivative and partial derivative, right? And so we can write in this form. And what it's telling us, if you divide it by dt on the both sides, we can get the acceleration, right? Because this is the change of the velocity, right? Then you do divide it by dt on the both sides, you can get the acceleration for this particle. Okay, will be dvp times dt, and then you get this one. Just have this additional dt here, additional dt here, and additional dt here, dt here, right? And be careful about these 3 terms, right? This dx dt, dy dt, dz dt. What this one? This dx dt, dxp dt is give you what? Give you the velocity of u velocity of this particle. This is dy p or dt give you v velocity of particle. This is dp or dt give you your w direction velocity of the particle, z direction velocity of the particle. Okay, you substitute this one uvw back to here. So what you get, you will see that, okay, the acceleration for this particle will be just equal to u times partial v partial x plus v partial v partial y plus w partial v partial z plus partial v partial t itself. Okay, so this is the acceleration. We get the acceleration of the particle. It's telling us that the acceleration of the particle including 2 parts: the change of the velocity field itself, and then this convection term. Okay, the convection, convective change of the velocity, because this is u, right? This is the change of this v vector due to this velocity field. Okay, we can also rewrite. We can define a new differential operator. We define a special derivative, this big D over dt, so that this big D over dt written in this form. Okay, and then we can rewrite this one. You can write this a over p just as dv dt, because that will different this one. You put this v here, you get this things will go back to here. Okay, and this derivative big D over dt we call it the substantial derivative. Okay, and you can sometimes you also call it the substance particle derivative, total derivative, and the substance derivative. Okay, material derivative, but they are the same thing. Okay, it's the substantial derivative. It is including the change on the time itself and also change due to the position. This is the change due to the position, right? This is change due to the time. Okay, So this is telling you that in this differential, in this translational motion, right? How we get the acceleration of this particle. Okay, just remember that this A of P is not equal to this dv dt. You may get confused, right? Because that acceleration should be dv dt, right? But why this is not equal? Because you can already find it here. It's not the same. Actually, your A of P is equal to dv of dt. This is substantial derivative. And this is regular. Why? Because that this v we have here, this v here is a velocity field. Is we defined in this Euclidean description. Is not defined in the Lagrangian description. So if we have the v defined in the Lagrangian description, then this will work. Okay. The reason why this is not working and we have this complicated description is only because this velocity v here, we write it in a velocity field, which means that we write it in this Euclidean description. We didn't use in Lagrangian. All right. And I will stop it here. And so we'll continue this topic on the Friday. All right. Do you guys have any questions? No question?
Professor?
Yes, I'm here.
You able to send out, say, like a Blackboard announcement just to confirm the dates for the homework?
Yeah, I will send an announcement today for both new due date for the homework and new midterm exam time. Okay.
Thank you.
No problem. And any questions, guys? No.
Oh, also, for homework 3, have we covered everything at this point that we should be able to complete it?
Yeah. The homework 3 is for the chapter 4. Now we are already in the chapter 5.
Okay, thank you.
Okay. Any question, guys? No question? All right. So if no question, I'll see you next Monday. All right. And remember that the new due date for the homework 3 will be next Friday. Okay. All right. Take care, everyone.